In this episode, we will talk about Step1X-3D, towards high-fidelity and controllable generation of textured 3D assets. You know, creating really convincing 3D stuff, the kind with textures that look and feel real, has been, well, a tough nut to crack for a long time.
Definitely. It takes a lot of skill, a ton of hours.
Right. Now, this research we're looking at today introduces something called Step1X-3D, and it's all about making that process easier and hopefully better.
Exactly. So we're going to dig into how Step1X-3D works, what problems it's really trying to solve.
And why it's actually a pretty big deal in the world of making 3D things, yeah.
Absolutely. The researchers really start by pinpointing the current roadblocks in 3D creation. And the main one, it's that we just don't have enough good quality 3D data.
Ah, the data bottleneck. We hear that a lot.
We do. And it's not just about the sheer number of 3D models. The usefulness, the utility depends so heavily on how good those models actually are.
Makes sense. Garbage in, garbage out, right?
Pretty much. They point out that in the open source world, there are actually very few data sets with more than, say, 10,000 samples.
Really? Only a few.
Yeah, the big ones they name are ShapeNet, that's got around 51,000.
Okay.
Objaverse, which is bigger at about 800,000.
Mm-hmm.
And then the massive one, Objaverse XL, that clocks in at over 10 million. 10.2 million, actually.
Oh, okay. 10 million sounds huge. Is that the solution then?
Well, that's the catch. While Objaverse XL is huge, it's scraped together from all over the web.
Ah, so the quality is a variable.
You got it. The quality heterogeneity, as they call it, is massive.
Yeah.
Think of it like trying to build a house with bricks you found scattered everywhere. Some might be perfect, others are cracked, misshapen.
Right. Completely unusable, maybe?
Exactly. And that inconsistency makes it much harder to train models that are robust and reliable. You're not just teaching it good examples. You might be teaching it all the flaws, too.
Okay, so it's not just quantity. It's that quality and consistency that really matter for these AI systems.
Precisely. And the paper also highlights something else important. 3D data itself is just inherently more complex than, say, 2D images.
How so?
Well, with a picture, you can often tell pretty quickly if it's good, right? You look at it. But in 3D, the shape, the geometry, and how it looks, the texture are usually separate things.
Right, they're modeled differently.
Exactly. And that separation makes it much harder to judge the overall quality. You could have a perfect shape with a terrible, blurry texture.
Or a great texture on a lumpy, weird shape.
Precisely. How do you even objectively say which one is better? It's tricky.
Yeah, it's like judging a sculpture just by its paint job, or a painting just by the canvas shape. They're linked but distinct.
That's a great analogy. And building on those challenges, the researchers note that the open source 3D generation ecosystem is still, well, kind of lagging behind proprietary company-developed solutions.
We're seeing progress, but there's a gap.
There is. They mentioned Trellis, for example. It's an open source model, which is great, but it has limitations in how well it generalizes, how well it handles new types of objects it hasn't seen before.
And that's linked to the data again.
Partly, yeah. It was trained on about 500,000 samples, which sounds like a lot, but it's smaller than what some of the big commercial players are using.
So scale of data really seems to impact performance in the wild.
It certainly appears that way. The paper also brings up the issue of restrictive release strategies. Some of the really advanced models, like Honey-1 3D version 2.0,
Okay.
they only release the pre-trained weights. You can use the model, but you don't get the training code.
Ah, so you can't fine-tune it easily or really dig into how it works.
Exactly. It limits what the broader research community can do.
Yeah.
It's like getting a fancy assembled engine, but no blueprints, no instructions on how it was built.
Yeah, that definitely slows down progress and collaboration if you can't tinker.
Absolutely. And one more key issue they raise. Many advanced models, even some open source ones, lack good conditional generation.
Conditional generation, meaning you can tell it what to make.
Right. It's common now in commercial platforms like Trippo or Rodan. You can give it specific inputs, text descriptions, reference images.
So you could type a photorealistic red sports car, and it tries to make that specific thing.
Exactly. Whereas many open source options might be more like, make a car, without that fine-grained control over style, color, specific features.
It makes them less versatile for actual creative work, I imagine.
For sure. So the authors wrap up this section saying, look, these problems, data availability and quality, reproducibility issues, lack of control, they're all interconnected, and they significantly hinder progress.
Okay, crystal clear picture of the challenges. So now let's get into Step1X-3D itself. What is this new approach? How's it trying to fix things?
All right, so Step1X-3D, it's presented as a feed-forward method for generating 3D assets. Key goals: efficiency and quality.
Feed forward. What does that mean
Yeah.
in this context?
It means it directly synthesizes the 3D asset during inference, basically in one pass. Unlike older methods that might need lots of optimization steps, refining things over and over.
So it's faster, like modern image generation models.
Much faster, generally.
Yeah.
Think direct printing versus manually sculpting each letter, like you said. Speed is huge for practical use.
Absolutely. No one wants to wait hours for one model.
Right. So the paper then breaks down feed-forward 3D generation into two main types, or paradigms.
Okay.
One is 2D lifting to 3D, and the other is 3D native generation. Step1X-3D falls into that first category, 2D lifting.
Okay, 2D lifting to 3D. Let's unpack that. What's the core idea?
The core idea is pretty intuitive, actually. It leverages all the knowledge AI models have learned from massive 2D image datasets.
Like understanding objects, textures, lighting from photos.
Exactly. And it applies that knowledge, or lifts it, to the task of 3D generation. It allows for transfer learning, tapping into that rich visual understanding from billions of images.
Smart. Reusing all that existing knowledge.
Very smart. The paper mentions this paradigm often involves reconstructing a 3D model from just a single 2D image.
From one picture? Wow.
Yeah. These methods typically extract visual features from the image using something like V2.
Okay, a feature extractor.
Right. And then they use architectures like vision transformers, or VITs, to generate the 3D shape based on those features.
VITs, right. The transformer models adapted for vision.
Exactly. They mention LRM as an example method that reconstructs something called neural radiance fields, or NERFs.
NERFs, yeah, those implicit scene representations.
Right, reconstructing those from image features. And they also mention another system, TGS. So essentially take a 2D snapshot, infer the whole 3D structure and appearance.
Sounds incredibly difficult. How do you guess the back from the front?
It is difficult, but these new models like V2 and the power of VITs have made huge progress.
Okay, so let's focus now on how Step1X-3D specifically handles the first part, generating the geometry, the shape.
Right, shape first, then texture. Makes
Yeah.
sense. Exactly. Step1X-3D starts with the fundamental 3D form. And a critical first step, given everything we just discussed about data quality.
Is cleaning up the data.
Massively.
Yeah.
They built a very rigorous multi-stage data curation pipeline. Started with that huge pool from Objaverse, Objaverse XL, ABO 3D Future, over 10 million models initially.
Wow.
And after all their filtering, they ended up with a high-quality training set of roughly 2 million assets.
2 million is still a ton. What did that filtering actually involve? Sounds intense.
It was pretty comprehensive.
Yeah.
6 main stages. First, texture quality filtering.
Okay.
They'd render 6 standard views, front, back, left, right, top, bottom, for each model, then convert the colors to HSV hue, saturation, value.
HSV color space, right?
By looking at the hue and value distributions, they could toss out textures that were too dark, too bright, or like really uniform, almost one color.
Getting rid of visually boring or badly lit stuff.
Exactly. And they also calculated perceptual quality scores and dropped the bottom 20%.
Okay, makes sense. What's next?
Next was single surface filtering. They use something called canonical coordinate maps, or CCMs.
CCMs?
Yeah, these maps help see if opposite views actually map to the same 3D point. If too many pixels did, it suggested the object was basically flat, like a plane or a thin shell, not a real volume.
So filtering out things that weren't truly 3D solid objects, like billboards.
Precisely, ensuring things had actual volume. Then came small object filtering.
Removing tiny things.
Right. If the main object took up less than 10% of the pixels in the front view, maybe because it was badly oriented, or just far away in a scene they removed it.
Focusing the model on clear, prominent subject.
Correct. Filter number 4 was transparent object filtering.
Getting rid of see-through stuff, like glass.
Yeah, things modeled with transparency, often using alpha channels in their principled BSDF shaders. BSDF stands for bidirectional scattering distribution function.
Okay, why remove transparent things?
Because they can mess up the relationship between the rendered color and the actual geometry. Think of like leaves on a tree represented by semi-transparent planes. Confusing for learning the solid shape.
Got it. Avoid ambiguity.
Next, 5th was wrong normal filtering. Normals are vectors showing which way a surface faces.
Right. Important for lighting and shape.
Crucial. They rendered normal maps and checked if any normals were pointing weirdly, like forming an obtuse angle more than 90 degrees, with a direction to the camera.
So finding surfaces facing away when they should face towards you, like bits that are inside out.
Good analogy, exactly. Identifying messed-up geometry. And finally, name and mesh type filtering. Just removing things explicitly labeled as point clouds because they needed solid meshes.
Phew, that is a serious cleaning process. No wonder they ended up with higher quality data.
Absolutely Herculean effort. So once they have this pristine data set, the next key step for geometry is converting the mesh into a signed distance function, or SDF.
SDFs again. Remind us what they are.
Sure. An SDF measures the shortest distance from any point in space to the object's surface. It's positive outside, negative inside, 0 right on the surface.
Okay, and why do they need that?
They need it to train their shape variational autoencoder, or shape VAE. And for SDFs to work properly, the meshes need to be watertight, topologically closed, no holes.
Like a solid container.
Exactly. They improved on an older method for this mesh to SDF conversion. The old way used a visibility check, basically seeing if the surface was visible from points on a grid.
Sounds straightforward.
It works okay for simple shapes, but struggled with non-manifold objects, things with holes, self-intersections, like a donut shape. The visibility check could get confused about what's inside versus outside.
Right, the hole in the donut isn't part of the donut.
Precisely. So they incorporated the concept of the winding number, drawing inspiration from another paper called Craftsman.3D.
Winding number sounds mathematical.
It is. It's a more robust way to tell if a point is truly inside or outside a complex shape, even with holes. They calculated this for points on their grid.
So a better way to define inside.
A much better way.
Yeah.
They combined this winding number check with the visibility check. This gave a more accurate occupancy mask, defining which grid cells are inside the object. This mask is then fed into an algorithm called marching cubes.
Marching cubes, right, that extracts a surface from volumetric data.
Exactly. And this improved process boosted their success rate in getting watertight meshes from the tricky Observer's data by about 20%.
Wow, a 20% improvement is substantial. Okay, so they have watertight meshes, good SDFs. What's the actual geometry generation model look like?
The core is a diffusion model. Specifically, they adapted a model called the Multimodal Diffusion Transformer, or MMDIT.
MMDIT. Inspired by models like FLUX for images?
Yeah, but modified to work with their 1D latent representation of the 3D shape. It uses an encoder-decoder structure.
Okay, standard pattern. What goes in?
The encoder takes two kinds of point clouds sampled from the mesh. One uniformly sampled, one sampled based on how salient or important the points are to the overall shape.
Uniform and salient points. Okay.
These get processed with self-attention, points looking at other points, and cross-attention, uniform points interacting with salient points, to create a compact, learned representation, the latent set.
Boiling the shape down to key features.
Exactly. Then the decoder takes a query point in 3D space plus that latent set and predicts the TSDF value truncated signed distance function, basically the SDF cap near the surface for that point.
Predicting the shape value at any given location.
Right. And the decoder also uses self and cross-attention. So they learn this compressed, meaningful representation of the shape.
Okay, how do they train this VAE?
Two main loss functions. First, a simple mean squared error, MSE, loss. It measures the difference between the predicted TSDF and the actual ground truth TSDF.
Makes sense. Minimize the error.
Second, a Kullback-Leibler, or KL, divergence loss. This encourages the distribution of those learned latent vectors to resemble a nice, standard Gaussian distribution.
I do that?
It helps make the latent space well-behaved, smooth. So when you sample new points from it later to generate new shapes, you get sensible results.
Ah, regularization keeps things tidy.
Exactly. Once trained, they generate a shape by sampling a latent vector, using the decoder to predict TSDF values on a grid, and then running marching cubes.
Back from the abstract representation to a concrete mesh.
Precisely. And they mentioned using hierarchical volume decoding to speed up that last step, generating the mesh more efficiently at different detail levels.
Smart. Anything else on the geometry side?
Yeah, one more piece for efficiency and stability. They also trained a rectified flow model.
Rectified flow. Different from standard diffusion.
It's an alternative. It tries to learn a more direct velocity field that pushes noise straight towards the target data distribution, rather than the step-by-step denoising of standard diffusion.
A more direct path from noise to shape.
That's the idea. They trained it using a flow matching objective, and they found that giving more weight to the intermediate time steps during sampling actually improved accuracy, because those middle stages were harder for the rectified flow model.
Interesting tweak.
And throughout training for both the VAE and the rectified flow, They used exponential moving average, or EMA, to update parameters, which helps stabilize things.
EMA, common trick.
Yeah. The whole geometry training was a big job. 2 phases, different settings, lots of GPUs, graphics processing units over many iterations.
Okay, so a very complex, computationally heavy process to nail the geometry. Now, the textures, how do they add the color and surface details?
Right, texture generation's another multi-stage pipeline, kicking off after the geometry is generated.
This makes sense. Stage 1.
First is geometry post-processing. Even with their improved watertight method, the raw mesh might have tiny defects. So they use a library called TriMesh to automatically fix things.
Like what?
Finding and filling any leftover small holes, ensuring it's truly watertight. Then they remesh it.
Remeshing, changing the triangles.
Yeah, they subdivide each triangle into 4 smaller ones and apply something called Laplacian surface smoothing. This creates a more uniform triangle layout.
Why is that important?
It helps minimize artifacts later at the seams of the UV map. The UV map is what flattens the 3D surface onto a 2D texture image.
Ah, okay. Preparing the surface for the texture map.
Exactly. And finally, they use a tool called Atlas to generate optimized UV coordinates, that 2D layout, and bake it into the mesh.
So sanding and priming the 3D canvas before painting.
Perfect analogy. Next stage.
Right?
Texture dataset preparation. And here, they really stress quality over quantity.
Even more so than for geometry.
Seems like it. From those 320,000 high-quality assets they had after cleaning for geometry, they curated an even smaller, super high-quality set of just 30,000 for texture training.
Only 30,000. Wow, what did they do with those?
For each one, they use Blender, the 3D software, to render those 6 standard views again, front, back, etc., but at a higher resolution, 768 by 768.
High-res views.
And crucially, alongside the color images, they also rendered albedo maps.
Albedo, the base color without lighting.
Exactly. Plus, normal maps for surface direction and 3D position maps for spatial coordinates. So, rich multi-view data for each quality object.
Okay, got this high-quality multi-view data set. Now what?
Now we get to geometry-guided multi-view image generation. The goal here is to generate consistent images from multiple viewpoints, given just one input view.
Generating the other 5 views from one.
Essentially, yeah. Using a diffusion model, which they call DMV, they built it on top of a pre-trained model called MV Adapter.
Using MV Adapter as a base, why that one?
It has advantages. It can generate high-res images, that 768 by 768 size, efficiently due to a memory-saving epipolar attention mechanism.
Epipolar, geometry-aware attention.
Sort of, yeah. It leverages the geometric relationship between views.
Mm-hmm.
And MV Adapter also generalizes well because it keeps parts of a huge pre-trained model called SDXL and uses a clever parallel attention setup.
So leveraging a powerful existing model, not starting from scratch.
Right. And the key part here is the geometry guidance. When generating those other views, they don't just feed in single input image.
They feed in the geometry info, too, the normal and position maps.
Exactly. Those maps they rendered earlier. They encode that geometric info and inject it into the MV Adapter using cross-attention.
So the model knows the 3D shape while it's painting the views.
Precisely. It helps ensure the generated textures align correctly with the geometry and look consistent from different angles. It understands the contours, not just the flat appearance.
Makes a lot of sense. But they mentioned potential issues still.
Yeah. Even with all that, discrepancies can arise between the 2D image space, where views are generated, and the 3D UV space, where the texture lives. This can cause artifacts like blurriness or seams.
Ah, so how do they fix that?
They introduce a texture space synchronization module. And importantly, this happens mostly during inference when generating a new asset.
A refinement step during generation, not training.
Correct. They contrast this with other methods like MV Paint or SyncMVD, which might need separate style transfer or refinement steps. Step1X-3D aims to do it within the single diffusion model. By aligning the latent representations of the different views, they argue their latent resolution, 96 by 96, is enough to hold texture details, and the model inherently learns coherence. So, no extra pipeline needed.
More elegant. How does the alignment work?
Okay, during the diffusion denoising process, for each step, they take the intermediate latent features for each view and unproject them onto the 2D UV texture map using the pre-computed UVs.
So putting the features onto the flattened texture layout.
Right. Now they have multiple versions of the texture in UV space, one from each view. They then fuse these together.
How do they combine them?
They weight the contribution from each view based on the viewing angle. Views looking more directly at a surface point get higher weight for that point's texture.
Smart weighting, like choosing the best angle for each patch.
Kind of, yeah. This fused, synchronized texture in UV space is then reprojected back into the latent space for the next denoising step.
Wow, okay, so it's an iterative refinement loop within the diffusion process, constantly syncing up the texture across views in UV space.
Yep. Exactly. A clever way to enforce consistency directly in the texture domain.
Very neat. So what's the final step after all this?
The final stage is bake texture. Pretty standard 3D workflow stuff here, reusing some tools from Untitled 3D 2.0, actually.
Yeah.
They take the generated multi-view images, upscale them to a high resolution, 2048 by 2048.
Getting those fine details.
Right. Then they inversely project these high-res images onto the 2D UV texture map,
Painting the final texture.
essentially. But even now, small issues might pop up: bits missed due to occlusion, slight inconsistencies leading to holes or breaks in the UV map.
Final cleanup needed.
So they implement continuity-aware texture in painting. It's an iterative optimization that fills gaps and ensures the texture is seamless while trying hard to preserve sharp details.
The final polish to make it look perfect.
Exactly. Making sure the finished 3D object looks seamless.
Okay, we've walked through the whole pipeline. Geometry, texture. How does Step1X-3D actually stack up against other methods out there? Do they compare it?
Oh yeah, they did extensive comparisons. Very thorough. Both against open source methods.
Like Trellis, Untitled 3D 2.0, TrypoSG you mentioned.
Right, and also against proprietary commercial systems like TrypoV 2.5, RoddenV 1.5, and Meshi 4.
Covering the field. How did they compare?
Multiple ways. Quantitative evaluations using objective metrics for geometry and texture quality, subjective user studies where people rated the 3D quality, and just visual comparisons, side-by-side results.
Covering all bases. Did they use a standard test set?
They actually built a specific benchmark dataset for this, 110 in the wild images. Some were examples from other 3D platforms. Others were generated by the Flux image model across 80 object categories from the COSIO dataset that's common objects in context.
A diverse set of inputs.
Yeah, and they systematically generated results using all the methods on this same benchmark set. That allowed for fair comparisons for the metrics and the user studies. The paper dives into those results, showing where Step1X-3D shines.
Sounds like rigorous testing. Okay, before we wrap up, did the authors mention any limitations of their current approach? Areas for future work?
They did, yeah. Very transparent about it. One limitation is the geometry grid resolution for the TSDF conversion. It's currently 256 cubed.
256 by 256 by 256 voxels.
Right. They acknowledge that increasing this resolution could allow for capturing even finer geometric details.
Makes sense. More resolution, more detail. Anything on the texture side?
Yes. Currently, the texture component mainly generates the albedo, the base color. They plan to extend it in the future
How?
to support things like relighting based on input image lighting and generating full physically based rendering, or PBR, material textures.
PBR, right. That includes maps for roughness, metallicness, things that make rendering much more realistic.
Exactly. So adding PBR support would be a big step for realism.
Okay, so good avenues for future improvement, as you'd expect in a fast-moving field. So bringing it all together, what's the big takeaway here? What's the significance of Step1X-3D?
I think the significance is really in the combination of advancements pushing towards that goal of high-fidelity, controllable 3D generation. It's not just one magic bullet.
It's the whole pipeline.
Right. The meticulous data curation, the improved geometry generation with the robust SDF conversion and the adapted transformer, the sophisticated texture synthesis with geometry guidance, and that clever synchronization. All these pieces work together.
Contributing to better quality and control.
Exactly. It feels like a really solid step forward in tackling those persistent challenges of data, quality, and user control in 3D AI generation.
Absolutely. It's genuinely fascinating seeing how they address these complex issues with both careful data work and some really innovative model design. It makes you think, doesn't it?
About the impact.
Yeah. Imagine the possibilities opening up in gaming, VR, AR, product design, countless areas, as tools like this get even better and more accessible. What future breakthroughs in this space do you think we should be looking out for?
That's a great question.
Something for you, our listeners, to mull over. What advances are you anticipating in this incredibly dynamic field? Thanks for exploring Step1X-3D with us today.